Now let us move further with some of the what you call basic data structures or elementary data structures before we move on to the complex algorithms in uh, uh, in this subject. So we will start quickly with the stacks and queues. Now, this stacks and queues you may already have seen in your data structures in second year, but let us revise and revisit this. Now, on your left-hand side, you have something known as stack. Stack, as you all know, or the term how a stack is defined, the one end of the stack is closed, and the elements or the items can be inserted only from one end. That is known as the top of the stack, and it works on the principle of last in, first out, LIFO. Last element which is inserted, that is the element which is taken out. Then comparing with the queues has both the ends open, and the elements are inserted from the rear end and elements are removed from the front end. Now, though, you can remove the elements from the rear end and insert the elements from the front end, but usually, or the way we proceed or progress, the way for flexibility, what we say and how the queues are defined is the elements are inserted from the rear end and removed from the front end. Now let us quickly look at the algorithm. The operations of stack operations, which are defined in terms of pseudocode. That's what we call it as algorithm. Now here we have the algorithm as add. You might have heard about the term push in your data structure, that is pushing an element on the stack. Now here in the prescribed textbook, what we have for design and analysis of algorithms, there the term add is used. So that doesn't matter. The functionality is same whether you are pushing an element or whether you are adding an element. In both the cases, you are inserting an element in the stack. Now, since this is the array-based representation of stacks, that is, we are taking array to hold the elements of the stack. So therefore, the very first case in the algorithm is we have to check if the stack is full. That is, if the top reaches n minus 1 or greater than reaches n, or if it is greater than n minus 1, that means the whole capacity of the stack is full, or that is the array what we have. Top has exceeded. Top is nothing but the index has exceeded the capacity, so we cannot insert the element. So we say that stack is full and we return false. That is, cannot push an element or we cannot add or insert an element in the stack. Now suppose in this case, if you see there are few more elements empty in the stack, so we have else. So we increment top index. So top, instead of pointing to this element, top is in moves to the next index. So this is over here, and then stack of top. Remember, assume that this array, the name is stack. Stack of top equal to item. That is the element we are inserting. So here we will insert. Let's say, suppose we are inserting 100. So top we have incremented. So top will now be pointing to, at this cell, and 100 will be assigned and return true. That is how the push operation happens or add operation happens. Now, before we move further, let us compute the time complexity of this add algorithm. What will be its time complexity? Now, can anybody reply? First of all, you need to know that you need to remember how to proceed. Now, earlier functions, when we found the time complexity, what did we do? We counted the number of steps or the frequency of each statement. So can you compute the time complexity? Or let's not say compute the time complexity. Let us say frequency of each iteration. Sorry, not iteration. Frequency or number of times each instruction gets executed. Can you do it? I'll show one example. Let's again go. What do I use here now? I want to write something. Is open mode here? Oh, open mode is there. What do I do? Show the desktop. Okay. Now what do I do? Okay. Now here itself, I'll just start scribbling something. Now this is going to take how much? 1 times. It will get executed once. Now if this is true, then this also will get executed once. There is no loop, remember. Here also it gets executed once. And we are not worried about these things, we are worried about these statements. This is statement, this is a primitive statement. It will execute only once. This is also a primitive statement. This also will execute only once. Return, that's a primitive. It also executes only once. So what is the total? 1, 2, 3, 4, 5, 6. So here we have 6 as the total. So if we consider this as a function f of n or time function f of n equal to 6, that means what? What is 6? This 6 is a constant. So we can say that this algorithm of inserting elements in the stack is taking O of 1. Oh, sorry. How do I rub this? It's taking O of 1. That is, this algorithm takes constant time, O of 1. Let me, where is the, okay. ये क्या आ गया भाई? How do I exit this? Okay, anyway. So this was O of 1, constant time. Then let us look at another function. So as we had a function known as push, the same way we have a function known as pop. So what is this pop function doing? The purpose here we say delete because the algorithm in the prescribed textbook it says delete, but delete and pop functions are both same. Just the name is there. Functionality is same. Absolutely, there is no problem. Now here, if we look at this function, I'll use a pen to write something over here. Now this function we need to see if top is less than 0. If it's less than 0, that means there are no elements in the stack. So we write stack is empty and we cannot pop anything. We cannot delete an element. We can delete only an element which is there in the stack. So when top is less than 0, nothing, we cannot delete it. If not, then stack of top. What is top? Pointing to this. So 15 is retrieved in an item. Then top will be this pointing. Top will now be pointing to this statement at this step. Then we return true. That is the element is deleted. So this is how your delete function or pop function or pop operation works for stacks. Now, can you compute the time complexity of this function? Just anyone tell me the time complexity of this function. We have already seen and demonstrated earlier classes also we have seen I mean, now also we demonstrated in the insert or the add method, add operation or push operation of stack. I have demonstrated how to compute the time complexity or the frequency of operations. Now you just tell me, what is the time complexity? For the first statement, if top less than equal to 0, how many times does it execute? Just anybody tell if you are awake or if you are listening. Just tell me, how much time will it take? How many number of times this statement executes? Anyone can unmute himself or herself and say, or just type it in the chat box. How much time does it take? It takes 1 unit because it's a primitive statement. Right statement, short statement is also primitive, it takes 1 unit. Even this takes 1 unit. Then this statement is also primitive, it takes 1 unit. There is no loops here. Even this is primitive, it takes 1 unit. Even this is there, it takes 1 unit to compute. So total is again 6, for which we can say that f of n of 1, which is constant, because 6 is not taken, this 1 is taken as a constant. Now, in the same way, if you consider the stack, let us look at this part. So last class we have seen the operations of push or add or pop or delete on stacks, and this stack was represented using arrays. So what all we performed here, like top equal to top minus 1 and stack of top is nothing but we are performing these operations based on the representation of these stacks and arrays. Now, the next thing is the same operations, that is push and pop on stacks, can also be applied when the stacks are represented as linked list. Now, if you remember in data structures, linked list is one of the data structures which has nodes, and each node has the data or the element, and the other part is the reference or the pointer to the next node, immediate next node. So if you consider this, here we have the stack. What we are saying is this stack is represented as a linked list. So the element 84 over here has a link to the next element, which is 47. To the 47 has a link to the next element, that is 21, 96, and 50, and so on. Now, in linear list, what happens is you can insert the elements at the beginning of the linear list, or the linked list, or you can also insert the elements from the end, as well as you can insert the elements from the you can delete the elements from the beginning as well as from the end of the linked list. Now here, since the operations of whatever adding or pushing or deleting or popping is performed at only one end in stack, so if we represent the stack using linked list, what we do is we usually say that we will be deleting, or we will be adding or inserting or pushing, and we will be deleting or popping or removing the elements from the front of the linked list or from the beginning of the linked list, because it's the only one end is open in stacks. So whenever stacks is represented using linked list, remember that instead of front or the head node, we call it as a top node, and insertion and deletion happens from that end. So here what we are doing is, if we have to push or add an item, temp is the new node created. So this is the node will be created here, temp. Initially top is pointing to the first node, and then we say that these are all the other nodes. So actually the arrows should have been on the opposite side. Sorry. There is a mistake in the representation here. The arrows should have been on the opposite side. Arrows. So yeah, this is the correct way. This is the correct way. So I'll just let me I let me make some changes here. The arrows actually has been in opposite direction. So again, I mean, it's going to be a problem in trying to understand. So let's yeah. Now this is correct. Sorry about it. So the top or the head position is always the front or the beginning of the linked list when stacks are represented. So we say that we will be adding or removing the elements from the top, that is the front of the linked list. Now a new node will be created wherever a new node has to be added or new element has to be added. A new node known as temp will be created. So this will be temp. A new node is created, although I don't have any value here, it will be blank. Then we check that if temp is not equal to null, that means they are, some elements in the node we can insert temp. Obviously, there is a space in the memory, that means. Though we usually don't have this operation, you might not have seen in stacks when you represented them using linked list. You may not have seen this condition here. But here what we have is, because we are designing an algorithm, we have to take into consideration every aspect and scenario. So what we are saying here is, if temp is not null means temp is created, a new node is created. That is, there is a capacity in the memory that we are able to create a space. Able to create a node that we have so much space. So anyway, if there is a space, that means we can create a node. Node is created already. Then temp arrow data, whatever item you want to insert. Suppose if I want to insert, let's say 20. So I'll assign data as 20 over here. Then temp arrow link, this temp arrow, this link, what you're seeing here, this link should point to top. So top will be here. And then this top will move up and will point to this node. So then return true. Else, if we are not able to, this temp cannot be created, then that means there is no space. So we say out of space and we return. So this is not the case when you have defined or created the stacks using linked list in your data structures. But here we have to take care, or the algorithm says that there should be a memory available. Only then we will be able to create a node. So whatever the reason might be, we will create a temp as a new node, and then its data will assign, and the link will assign to the top and move top to the point to that node. So a new node will be added at the front. In the same way, what happens is delete also is the same thing. Now here what happens is delete or pop method, we check if top is equal to null. If top is equal to null means it is not pointing to any node, that means the stack is empty. Then we return false. Now else what happens is, if suppose this is top, this part is top. Now suppose this part is top. Now suppose this is top, 15 is the top element. So we retrieve the element from top arrow data, we get the item there. And we will take a temp as the reference variable or a variable or an object, I suppose, which stores. So 15 top and temp will be pointing, both will be pointing to 15. Then top equal to top arrow link, that is top will move to the next element, that is 96. And then you can delete temp, that is element 15 can be deleted. So this is how stack works, or the operations of stack using linked list works. Now you have already seen this in data structures. We just have to brush up these aspects. Now let us try to find the time complexity of these two functions or algorithms. That is, we already had seen last class time complexity of add or push method or algorithm and pop or delete algorithm when stacks was represented as arrays. Now in the same way, even here, if you look at this, let me take a pen. If you look at this method, then this add method is when stacks are represented using linked list. So this statement is going to take unit of time. This is if statement, obviously it takes unit of time. Anyway, I'm just write it. There is no loops. This is a basic primitive statement, takes unit of time. Even this statement takes unit of time. Even this statement takes unit of time, because these are all basic statements. Then we don't have to bother about this out of space and all, it doesn't matter. Even if we add up, it doesn't matter, it's going to take constant. So the total is 1, 2, 3, 4, 5. So it's nothing but when we have 5, this 5 is order of 5, which is nothing but O of 1, or we say that it's constant time complexity. So it's the time complexity of this algorithm is constant. Then let us take the next one, the delete method. And delete method, these statements are primitive statements. Doesn't matter if because it takes only 1 unit of time. I mean, though it executes if there is no element, but the main important statements are these statements in the else part. So this statement, this primitive statement, take 1 unit of time. Even this takes 1. Even this takes 1. Even this takes 1, as well as this takes 1. So on the whole, we have 1, 2, 3, 4, 5. So instead of that, you have 5. It's constant. So instead of that, what we say is it is order of 1 or big omega of 1. So so remember that whether stacks are implemented using arrays or whether they are implemented using linked list, the add and delete operations both will be taking unit of time, that is big O of 1 or order of 1 as the time complexity. And let us move further. Let us talk about queues. Now, if you here the textbook or the syllabus more focuses on circular queues rather than queues. And with respect to stacks, in comparison to stacks, here we are not talking about whether the queues can be represented using linked list or using arrays. We don't have any problem when the queues are represented using linked list. But there is a problem with respect to memory utilization when queues are represented using arrays. So here, I mean the textbook or the syllabus, we only concentrate about queues through which the elements can be stored and the operations can be performed based on the array representation. Because there is no problem with respect to linked based representation as far as the memory is concerned. Now what happens is, if I go back, let's say that, let's see the first slide. This is, let's say, this is our queue. Now what happens is, in queue, the operation, you all know that the elements are inserted at the rear end and removed from the front end. So in normal basic operations when we perform in queues, when initially front and rear will be pointing to the initial part, then rear will be incremented and an element will be added. Front will be pointing to that node. So first time the front and rear will both be pointing to the same element because there is only one element at the initial state. Then rear will be incremented and then next element will be added. Again, rear will be incremented, another element, so on and so forth. Let's assume that we have 5 elements here. Now, in an array, obviously, we all know that there is a capacity for an array. In an array, there is a size for an array. So the maximum number of elements that we can store for a stack or a queue is limited to that size. And in stack, there is no problem because we will always insert the elements from the rear end as well as remove the elements from the rear end when array is considered. But whereas in queues, we insert from the rear end and remove from the front end. So now I have started inserting it. And then suppose if I insert another element, let's say 16. So rear will move here. So this will be rear. Then 17, I add 18, I'll add. So ultimately, this rear is going to come here. This rear is going to rear is going to come here, that is, rear will be pointing to this. Now, if I try to insert another element like 20, will I be able to insert? No, because the size of the array is full. So the whole capacity is exhausted. Now, if I remove an element, say 84 is removed, so what happens? Front will not be pointing to this, element, front will be pointing to this element. So this will be empty. If I remove another element, 47, let's say, so front will not be pointing here, front will be pointing to this node now. And these two cells are, what do you call it? They are empty. But suppose if I now try to insert an element in the queue, I have to increment rear. When I increment rear, there is no sequential space here available here. There is no space available here. Array size of the array is exhausted, so I will not be able to insert an element, even though there are some spaces empty at the beginning of the queue, or at the beginning of the array. So I will not be able to insert the elements now, even though I have space, because the rear has reached the capacity or till the end, the length of the or the capacity of the array. So I cannot increment an rear pointer and insert it, because I will not be able to insert in that place. The capacity is has reached that limit, even though I have some empty spaces or empty cells remaining in the array. So this is the problem. So in that case, what we do is, instead of this one, what we consider is, this is like a circular queue we consider. Circular queue. It's a cycle. So when rear is incremented, rear, instead of creating a new space here, this rear pointer will come and will be pointing to the first element. So this will be rear. So these type of queues are known as circular queues. So that is what we have it here. That is what we have it here. Circular queues. So in circular queues, what happens is, you start from 0. Let's say if you start from 0 or 1, whatever it is. I can store element J1, J2, J3, J4, J2, and all these things are considered in circular fashion. Last element will be n minus 1. Now I have started inserting here. So I can say that this is the front of the circular queue, and this is the rear of the circular queue. Now what I can do, I can start adding element here, element here, element here, till I can fill it up. So rear suppose can point back, and I can remove. So the cycle continues for rear. I can continue the rear cycle, start deleting, or even start inserting. Now obviously, when all the elements are full, that means even this is if rear is pointing here to this, all the cells are occupied, that then queue is full, obviously. But suppose if I start deleting, so front will not be here, I delete one element, two element, no, so a front will point here. So what happens, even if things are full, these two elements might be empty, and rear, if you increment the rear, since it's a circular queue, rear will be pointing here. So it forms like a cycle there. The front and rear can move along. But remember that if all the cells are full, even here, we cannot insert. But the circular queue gives us the flexibility of incrementing the rear value and using the empty cells which may be there at the beginning of the queue. Now, this is another thing, example. So what it says is, there is no fixed front and rear. Now this keeps on moving. You can store elements from this also, this 0, and then n minus 1, n minus 2, that way you will be able to store it. So circular queue, what this diagram is same as this. There is absolutely no difference, except that the elements are stored at different locations in both of them. So this is what is the circular queue. Now the operations, obviously, it is known as enqueue or add on queues. And remember that we are taking circular queue into consideration here, and stack based representation. So NQ is to add element in the queue. So whenever you are adding element, you will not just do rare plus 1, but you will do rare plus 1 mod n. N is number of, or the number of cells, or the capacity of your array. So mod n means whatever rare value you start increasing, mod n will give you the remainder one. So you will be within the range, and the rare pointer will not exceed the array, but once it reaches n, it will now be pointing to the 0th element. So mod n is used to move in circular fashion, move the rare pointer in circular fashion, or rare index in circular fashion. Then we will check if front equal to rare. That means obviously front is equal to rare. When the rare comes front, both are 1. That means all the cells are occupied. So we say that queue is full. Otherwise, if front is 0, that means there is no elements in the queue. Queue is empty actually. So rare becomes n minus 1. Else, if front is there, then rare equal to rare minus. Now here there is still, when front equal to rare, we will not be able to insert the element. So queue is full. Well, that is one point. And if queue is full, now what we can do? We just cannot. Front is equal to 0. That is only first position. Front is at first position, and rare is also has a reach still. So rare, we just don't add this, make this rare. Rare, we make it n minus 1. We make it back. So actually, rare was at this place. Rare was at this place, and by performing this step, rare was pointing to this place. The rare was pointing. Assume that this is also filled up with J0 something, pointing to this step. Now, once if front is 0 itself, front is also pointing here. If this is the front is also pointing here, then whatever rare was incremented, we will get back rare to the original position. Because again, next time also we have to increment and perform the mod operation. Else, if front is not 0, front is not 0, what happens is rare will be rare minus 1. So if front is pointing here, suppose if F was here and R was here, rare were here, R rare was here. So with this, what happens? Rare will be pointing to this part, front itself. Now front is not 0 means we have to get back rare to, rare was 3 means rare minus 1, which is 2. So again rare has to come back here, so that in the next operation we will be able to know what is there. So in this case, both, in this scenario, we are not able to insert any item because the queue is full. If queue is not full, then rare, this item is assigned to the index wherever rare is pointing. Now rare is actually pointing to this. Using this expression, the rare points to that index, and we return true. So this is how we implement the NQ method to add the nodes. I add the elements in the queue when a queue is in circular fashion, represented using stacks. Represented using arrays. Now, same way as we have added, we also have a method known as delete, that is DQ method. In this DQ method also, we see whether front is equal to rare or not. If it is equal to, that means queue is empty. There are no elements, both are equal. If not, then we increment front because we are deleting from that. But we use mod 10 because it's a circular queue. Whatever increment happens, it has to be mod so that we end at, we are within the range of indexes for our circular queue. And that is the front index we get, and we retrieve the queue of the front, whatever element is there, we return true. So this is very simple rather than adding the elements. But always remember that just don't just try to add rare plus 1 and we just don't do front plus 1 as in normal queues. But since this is a circular queue to save space, we perform the mod operation both the ways in rear +1 mod n as well as front +1. Over here, as we have seen, rear +1 mod n as well as front +1 mod n. So we have mod n so that we are within the range of the number of elements what we have in the array. So this is what is circular queues about.